Today we're going to dive into fats and carbs because if all the macronutrients, these are probably the most confused ones out there. At the end of the day, you start to wonder what you're supposed to eat. I hope that today, as we dive into fats and carbs and the structure of these molecules and how similar they are, you're going to realize that these arguments are extremely antiquated and were probably never well founded. To give a sense, again, as I love to do, of how we came upon these mistakes, it's worthwhile to consider the synergy between social norms, social activities, social behavior in America, and the pseudosciences that were emerging from the nutrition world. In the 1950s, we began an engineering process where we started to imagine a world both at the soil level and at the food level that was dominated by the oil and gas industry. Ironically, just as we had with the pharmaceutical explosion in the early 1910s and 20s when we discovered we could make oil into drugs, we were starting to realize that we had underestimated the potential to create chemicals and chemical extracts from all kinds of weird building blocks within our food system. So the same chemistry that we were using to modify oil and gas into chemicals that would treat our soils or chemicals that would become drugs to treat our bodies, we were learning to manipulate the building blocks of carbohydrates and fats within our foods to create completely new compounds that we had never seen before in the human diet. We developed things like margarine, a fake butter. We developed things like high fructose corn syrup, a bizarre extract from a sucrose molecule in corn into an abnormal ratio and abnormal structure of fructose and glucose. And so we created these fundamental new building blocks that had never occurred in the human body before, and we did not have the metabolic pathways to correctly process these new chemical molecules that were being introduced in extremely high volumes to the American diet. Even beyond that, we created things like monounsaturated and polyunsaturated fats through hydrogenation. So hydrogenated oils that you find in the margin was also the same oils that we were using for cooking oil suddenly. We were taking things, a naturally occurring canola oil, and then hydrogenating it into this, mono or polyhydrogenated oils, which again were creating these bizarre structures in these carbon chains that we had never seen before. Simultaneous to the development of this new synthetic chemical food system that we were starting to imagine there in the 1950s and 60s, we were also developing the chemical agricultural system of nitrogen, phosphorus, potassium fertilizers from fossil fuel. So we were taking fossil oil reserves out of the ground and turning them into nitrogen-based fertilizers for soil systems. And so the NPK fertilizers became a boon, and it was actually called the Green Revolution as the chemical industry became the primary input source for soil systems in the first time in history. Previous to that, of course, we had used methods such as crop rotation, cover crops, composting, and the like to increase the nutrient density within the soils of the world to encourage vigorous plant growth. But with this advent of NPK fertilizers, we realized we could be far more lazy, if you will, and another word for that is efficient, far more efficient in our management of soils, where instead of having to compost and do all this complex cover seeding and multiple passes with chemicals or otherwise to kill those things, they started just using the NPK fertilizer as a primary nutrient source to create green plants. As the NPK term would suggest, it's missing most of the rest of the periodic table. So suddenly our soil systems were fundamentally lacking all of the micronutrients and macronutrients and elements of minerals and everything else that it would have gotten if we had continued crop rotation, high intensity grazing practices, the cover crops and the rest. We gave that up for this simplified thing of three inputs, the NPK, nitrogen, phosphorus, and potassium, and used that as an excuse to start to go to mega farming. So we were growing farms that were not 300 acres anymore, but 3,000 acres, and eventually today we find farms that are 30,000 acres. And so this is possible when you stop taking care of the soil and use just simplified chemical inputs. This was not too indifferent than what was happening on the nutrition side, where we were starting to fail to get those nutrients out of the soil into the plant, and we were starting to see a monotony of nutrients within the plant itself as we dumbed down the soil systems. Unbeknownst to us at the time, we were also undermining the very fundamentals of life itself through diminishing the microbiome within those soils. Bacteria, fungi, and their incredible combination and their incredible co-creative capacity with plant fibrils create something called mycorrhizae. The mycorrhizae and the mycelium of the fungi are these extraordinarily bizarre three-dimensional structures that are so good at taking the periodic chart, all the minerals in the entire planet, and turning them into unique nutrient sources. And so the beautiful thing about intelligent soil is whatever that plant needs, whether it be a tree or a tomato plant or basil, whatever you're growing, the soil in combination with this rich microbiome can always figure out its optimal nutrient input if it has that intelligent connection. As we started overplowing as far back as a couple thousand years ago, we were using methods for disrupting soil, and then the classical plow that you see on a farm today was invented in about 900 AD. And at that time, we saw the birth of what we now call Western civilization. So if you pick up any Western Civ 101 textbook, the first paragraph is likely to say something like, Western civilization began with the invention of the modern plow. What we were doing with that plow was destroying the three-dimensional structure of the mycelium and mycorrhizae and their relationship to the plant fibrils. And so as far back as 1100 years ago, we were starting to decrease the fundamental nutrient density within food. And then as we started into the industrial age and the acceleration in the 1700s into the 1800s, and especially in the late 1800s to the early 1900s, we saw fundamental accelerations in technologies that were accelerating the death of the soil. This, of course, the United States led to the massive Dust Bowl of the late 1920s and early 1930s, when we had so thoroughly killed our topsoil that it had turned into just a dead dust. It could no longer grow plants, and it was blowing all over the Midwest and burying towns quite literally in these massive dust storms. It turns out that, almost 80 years later, we are creating the same phenomenon through a chemical input system that's killing that same microbiome that we had struggled to recover after World War II. And we're doing it now, instead of overplowing, we're doing it through over-chemicalization. Overplowing is still a problem on a lot of organic farms that have stopped spraying herbicides and pesticides at the same rate. In effort to decrease the herbicide input, they start overplowing again, and they can destroy their soil structures even more severely sometimes than the chemical industry can. And so these combinations of overplowing and chemical input management can easily destroy that fundamental health of the soil. As this kind of marched along, by the time we were hitting the 1960s and 70s, humans for the first time were eating food that were fundamentally deficient in the nutrients that we needed to make enzymes function within our body. The enzymes even that would create the energy from those long carbon chains, fats and carbs and everything else, we were failing to metabolize energy in our bodies. Certainly within the human cell, but also in the bacteria and fungi of our gut. Our gut microbiome was starting to be damaged and oversimplified by this loss of nutrient input. Inside the human cell, the mitochondria, tiny little bacteria that produce the energy from sugar and fats into a small molecule called ATP, and in so doing release that sunlight energy inside of our cells. That whole process started to get poisoned, both in plants and animals. Not surprisingly, in the plant kingdom, when we started to diminish the nutrient density and the vitality of metabolism in the plants, they became vulnerable to disease. And that took on the form of invasive weeds that would encroach on them and knock out their fuel sources and nutrient sources within the soil, or invasive insects that would come and consume those weakened plants. And so we then made a call for help to those same chemical companies that rushed in to give us more versions of herbicides to kill the weeds and pesticides to kill the insects, instead of just asking the simple question of why are our plants more prone to disease in the 1970s than they were in the 1940s and 50s. And so it's a very bizarre kind of lack of root cause analysis that was sneaking in to destroy the metabolism of plants and humans. Not surprisingly, The human chronic disease epidemic comes along at the same time that our plants are starting to fail in their immune system. And so we started to see the advent of obesity, 1970s and 1980s, as we got more and more aggressive with our chemical inputs. The herbicides really took a revolution there in 1976 with the widespread use of Roundup, which was the first widespread use of glyphosate, which is a compound that chelates or locks up minerals within soil and living systems so they can never become bioavailable. And so we started spraying our soils and our plants ultimately with a compound that locks away nutrients. Any nutrients left from the dead and dying soil are further locked up by this glyphosate compound. In addition, glyphosate blocks the production of amino acids, which become the building blocks for proteins. And so in a single chemical application starting in the 1970s, we were taking away the building blocks for the structural proteins within bodies and enzymes and everything else in our body, and diminishing their fuel and nutrient sources at the micronutrient level by chelation and poor soil management. What happens when you start to undermine the amount of nutrients within any gram of food is the body needs to consume more of that food to get the same nutrient result. Unfortunately, in the 1970s and 80s, as obesity started to emerge as an early epidemic, it was tiny compared to what we see today, but it was starting to be recognized for the first time as a real public health threat in the 1980s. And we immediately boiled it down to this basic argument that it must be too many calories. And certainly Americans were being given the capacity to consume more calories than they ever had before through the processed food system. So we had things like high fructose corn syrup and the artificial oils and all these weird things that were packing calories inside of our food artificially. We had gotten away from whole food systems. If you consume whole foods, whether it be a whole plate full of veggies and squash and legumes and all of this incredible, milieu of nutrients, you can eat, thousands of calories of that and get a massive download of your micronutrients in a day. But if instead your plate looks more like a simplified, genetically engineered russet potato and a big, hamburger that's infused with weird hydrogenated oils and soy extracts and flavorings and all of this, you can get a lot of calories, the same couple thousand calories, with almost no microminerals and micronutrients in there. You're missing manganese and zinc and all those other critical ones that we looked at when we looked at mineral salts as part of the diet in the last segment. And so we were starting to get calories without nutrients. And so it wasn't that the body was suddenly going after more and more calories for the sake of getting obese. The body was having to eat more and more food and therefore more and more calories to get the micronutrients that it was critically needing for function. The body doesn't eat just to go after calories, and that's a very important realization. We tend to think that the brain is simply counting calories in and calories out and will match those just so that you can do it. But ultimately, you need to get as many calories as it takes to get the nutrients within the food. And this is the difference between that experience of eating from your backyard garden, where if you make a salad from your backyard and you've got homegrown lettuces and mints and herbs and spices thrown in there and everything else, you try to eat that whole big plate of salad and it's actually hard to finish because your body has got so much nutrient density within that food. Contrast that to going to a restaurant, ordering a salad, and they give you a massive pile of iceberg lettuce that was grown hydroponically, never even touched soil, and it, completely deficient in these things as it was grown under a conventional chemical farming methodology where the minerals were chelated and everything's kind of dysfunctional in there. And you can eat that through that salad in a few minutes and be ready for your next dish because there was no nutrient density for your body to process. Your body's whipping that through the small intestine, waiting for something real, waiting for something nutrient dense that's going to put it to work and get the extraction process going. And so Americans in the 1970s, 80s started eating more food to get after the diminishing amount of nutrient within the food. At the same time, the use of sugar, fat, and salt combinations, as we started to get purified sugars, things like high fructose corn syrup, combined with purified salts like sodium chloride that we just covered, combined with very drug-like qualities of fat molecules, we had discovered how to create a cocaine response in the brain. And so when that highly processed fat, sugar, and salt combination hits the stomach, it creates a neurochemical event in the brain that looks like cocaine. And it encourages the person to eat more. It shuts down the satiety center, creates a pleasure experience, and the person suddenly starts eating with 2 hands instead of 1. If you sit around a table, you can observe this quite easily. Again, do that giant, salad from the garden, maybe a good glass of wine if you want, and some homemade bread. Put that on the table and watch the community consume that. There will be conversation, there will be a sense of relaxation, there will be a sense of joy, and that incredibly French experience of joie de vivre there that emerges from that chemistry of social and food magic that can happen there. In contrast, you take that same group of people and you go to a fast food chain, you go to Red Robin or McDonald's or wherever you're going to go, and watch the behavior. In those first couple of minutes after the food is delivered, there's almost no talking. Everybody moves very quickly to a 2-handed eating approach, where no longer is it a thoughtful experience of tasting each bite and the explosion of flavors of all the herbs and spices from the garden on top of the nutrient-dense lettuces and all that, where the body is processing it and you're having a spiritual space to communicate. Instead, as soon as that cocaine response kicks in, your body says, give me more of that. And suddenly all of your attention zooms down to consuming as much of that on the plate as possible. So the amount of conversation decreases and all of this. And so you can see this almost in every single restaurant where things are buzzing and you're starting to have a social experience. Everybody's ordering food, but they always forget to order the food because they're so busy talking. And so the waitress comes back a few times to say, hey, did you get a chance to look at the menu? I worked in a restaurant when I was in college, and I remember how frustrating it was when people were having so much fun together. It was wasting my time, and I was failing to turn my tables over because they hadn't even ordered yet. They'd been there for half an hour. They finally order. They keep chatting. It's a beautiful time. They've got a couple glasses of wine in. Things are going great. And then the food gets there, and suddenly there's silence at the table. If that's the experience in the restaurant, you know they've delivered the fat, salt, sugar combination in some form that's giving you a drug response to the food rather than a culinary experience, rather than that kind of spiritual upload that can happen when you get a nutrient-dense, nutrient-diverse food on your plate. So for all of these reasons, socially and culturally, we began to lose the culture of food. And I think that's what really led to the obesity epidemic in a lot of ways, is as we started to increase the likelihood of that salt, fat, sugar combination on any piece of food, Starbucks being a bizarre example of this, right? And so now we've got coffee in the morning that is creating these salt, sugar combinations and fat that will trigger those cocaine responses. A Starbucks drink, I'm not a coffee drinker, but I go there and I'm always getting my matcha latte there, and I'm listening to the orders coming before me, and I couldn't even repeat them to you because I don't even know the words, but it's like caramel macchiato something or other with a double espresso of this and that, and it's so confusing to me, like how we got coffee to this point to be able to carry 900 calories into the consumer as their first intake of the day. And there's piles of whipped cream on top of the coffee. I mean, it's obscene what we've done to coffee out of this kind of consumer drug dispensary that we call Starbucks. And so that has kind of trickled into all areas where we've learned to do this. And one of the devastating effects, going back to that table of people that aren't talking to each other, instead just rushing for the cocaine, is that we started to eat alone, and we started to lose community around food. And certainly other social changes started to happen. Television went from 3 or 4 channels when I was a kid to 300 channels in the 1980s. And suddenly, there's cable, and there was a whole phenomenon. All cable companies were in a contest to see how many channels they could pack into your monthly cable bill and all of this. And then, of course, the more recent advents have gotten totally out of control with all of the streaming platforms and everything else. But it's perhaps not coincidental that we started to create content demand, at the same time we were creating drug experiences on the plate, because in that cocaine setting, you don't necessarily want social interaction, you want more stimulus. And so we started to create faster and faster content. And if you look at, you know, the news that I grew up with when I was a kid, which was like the what was it called, world news once a week with, you know, Tom Rather, one of these guys, it was so slow. Like, you know, it's one guy's face, no cuts. He delivers, you know, the headlines and news, and maybe it breaks away at some point for some B footage out in the field with one of their anchors or something like that. Now you look at CNN and they've got a cut every, you know, 2 to 3 seconds at the longest, and oftentimes even a couple cuts in a single second, where your brain is getting, you know, just inundated with stimulus. And so we have become drug dependent in the whole experience of food. At the same time, we became, you know, a drug delivery system through media content. And now some 50% or more of the meals that Americans eat are alone in their car or on their couch. And so that's a frightening thing for me. And it's really, I think, starting to get at the underpinnings of why did the obesity epidemic happen. Certainly there are, you know, biochemical reasons for it, and there are stress factors that increase the likelihood that your body starts storing all of its calories as fat and things like this. But I think it was really this transition from nutrient intake to drug intake, from community around food to isolation and consumption in isolation of our food. And so this is the crisis we're currently in socially, and it was leading to this obesity epidemic. And the simple conclusion that the food industry was able to do was tell consumers, well, fat equals fat. If you start eating fat, then you're going to get fat. This is so erroneous, it doesn't make any sense in any part of history until we started processed foods and started breaking real food apart into these drug-like qualities of purified fats, purified sugars, purified salts, and that's when we started into the drug campaign. But fat does not equal fat, and you can see this every single day if you watch sports, or a great example is the Olympics, right? You're watching the most elite, most successful athletes on the planet, and the amount of calories they consume in a single day is phenomenal, right? And so if you look at the swimming competition, Michael Phelps being the most decorated, you know, Olympian in history, I don't know how many gold medals he has now, 28 or something ridiculous, most decorated, you know, lean muscle machine, you know, athletic machine that we've ever produced as a human species, and he's eating somewhere around 9,500 calories a day. 9,500 calories a day, and at least half of that is in fat. And actually a relatively small percentage is in protein. So proteins, fat, and carbs, and he's not even eating well. Like, it amazes me when, you know, I think he's gotten better as he's gotten older, but historically he was eating, you know, processed bread with turkey sandwich and 2 bags of Doritos. Like, he was eating kind of crap food, but his body was so revved up due to the exercise physiology he had created within his body. He had learned how to release all of the energy that he was taking in into that light energy that would fuel the muscle, the brain, and everything else. So his reaction time, his muscle recovery time, his muscle tolerance to the exercise in the first place, all of these things were ramped up through a learning process of cramming fuel into the body and releasing that fuel. What his mother did right, and people have argued whether she could have fed him better or anything else. As a kid, he learned to eat, you know, relatively processed diet. But what she did really well, I think, not knowing that family enough to really comment on this, but what I see in any athlete that's been able to achieve that is at some point they were able to see food as fuel instead of food as a drug or food as the enemy. And so this simple conscious awareness that food can be the energy for life is a very critical step in the way in which we ultimately process those nutrients in our body. And so fat cells, you know, or dietary fat intake being taken into Michael Phelps will never turn into fat. He's determined at the psychological level and at the cellular metabolism level that everything coming in is in abundance and should be burned right away for maximum performance. Contrast that to somebody who is living a lifestyle of a sense of scarcity at the cellular level, where they're intermittently eating, they don't eat, some days they eat like crap and they only get in 1,500 calories, or maybe they go on a diet and they get 600 calories, and then the following week they start emotionally binge eating because they broke up or they saw a rom-com that made them feel insignificant or whatever it is. And so now they're binge eating and they'll get 3,000 calories in a day. It's that variability of fuel intake where the body doesn't know, am I starving? Am I not starving? Is there plenty? Is there not? And as that person starts to go into a fuel storage process due to a fear of famine, due to a sense of the brain and at the physiology that there might be scarcity, we start to store fat. And that can be from sources of sugars or fats that we can go and convert that to visceral fat. We can take either of these carbon chains that would be sugars or fats and put them into that storage process. So let's imagine that person who is not feeling like they're living their highest life, does not feel fulfilled as perhaps the athlete does, who is every day focused on doing their very best at something and know they're at the peak of their entire global competition, and they feel fulfilled because they know they're doing their highest good. They're at their peak performance. Contrast that to somebody who is on the couch and feeling depressed about themselves and is starting to get overweight, and suddenly everything turns into a vicious source of stress. When the hypothalamus, deep in the middle of the brain, starts to send stress signals down to the pituitary gland, it sits at the base of the brain, and we call it the master gland in the endocrinology field because it controls your adrenals, your ovaries, your testes. It controls your visceral fat storage, controls all kinds of different processes throughout the body, thyroid, etc. And that master gland starts to shift its messaging to the liver and kidneys, thyroid, and everything else to tell it that it's in a time of stress. There's war, famine, pestilence, something is going on to put this creature in a state of stress, and it starts sending signals to the liver to make sure that sugar and fat coming into the system is stored as visceral fat initially, which is fat stored in and around the abdomen, which is the most inflammatory fat, certainly associated with the kind of inflammation that then drives heart disease downstream and everything else. And so we start into this kind of chronic disease event with the relationship between stress, storage of fat, and inflammation. And so that's where we were in the 1980s, and it was too easy for the food industry to say, well, if you eat fat, you're going to get fat. It was so simple of an equation for the consumer that it was easy for us to be duped into a completely new industry of processed foods called the low-fat or fat-free movements. So in the 1980s, we see this explosion of low-fat and fat-free compounds on the market. Low-fat milk, low-fat butters, low-fat oils. It went on and on. And as that craze happened, what happened is people who were already in a stressed state started consuming more and more processed versions of fat, losing the natural balance between fats and carbohydrates in something like a plant structure or something like that. They started to go to these highly processed foods. Low-fat yogurt was a big one I remembered always being in my house. There's this belief that the fat was making people fat. And so in this bizarre way, the chemical industry created a problem and then created an actually worse version of the problem by increasing the amount of processing of all of our whole foods to give us the perception that we were doing something healthy for ourselves. And so that really pushed hard through the 80s and 90s. Finally, as you start to see the reaction to that realization, what we had done, we started to back off in the 2000s. You see less and less of the low-fat and no-fat stuff on the shelves, and you started to see different versions of processed food that we can get to later. But the sugar industry was doing the same thing to us, okay? And so we were starting to be concerned about the amount of sugar consumers were taking in, and so we started the diet sweetener industry. And we did the same thing again, created a problem through fat, salt, sugar behaviors, isolation from cocaine response, social change, all of this stuff happening, and we created the bigger problems of the fat-free and the sugar-free kind of phenomenon. And the chemicals that we ended up creating to be in those fat-free and sugar-free substances became real harbingers of massive amounts of inflammation potential. And we saw the explosion of chronic disease accelerate again in the 1990s into the 2000s. And so it's just been this extraordinary slippery slope for the American consumer, further and further away from the nature of our food. So I want to get now to really the fundamentals of what these molecules look like and how they're utilized in our body so that we can maybe find our way out of fear for fats and carbs and realize that they are simply nature's way of getting sunlight into your body and releasing that energy from the battery of these carbon molecules to make you run at your optimal state. And if I can get you back to a state of realizing that the food that you are growing in the backyard no longer has to be considered carbohydrates, proteins, or fat, but all of it was designed perfectly for the metabolism throughout every stage of the microbiome within your gut, to the liver within your body, to the bloodstream, to the distal cell, to the clearance of the metabolic downstream products through the kidneys out into the urine. That whole journey was created in perfect harmony with mammals and other animals, multicellular life as a whole, by the intelligence of the way in which life would emerge over a 4 billion year process of kind of perfection and advancing of adaptation capacity, and always the search for biodiversification within biology. And so I want to take you out of food fear, put you back in a relationship with nature and your food system to get you there. So a quick look at fats. This slide here is showing you a simple saturated fatty acid, and you see all those C's lined up in that kind of backbone there, and then the H's hanging off of them at each point. That is a simple fatty acid called saturated fat, and it's saturated because there's hydrogens. There's 2 hydrogens on every single one of those carbon backbones. On the left side, you see a carboxyl group, which is carbon with 2 oxygens and the hydrogen there. And so that little carboxyl group is what creates the acid side of it, of the chain there. And so a fatty acid is a carboxyl group with a long carbon string that's storing energy within the carbon bonds. So the little bar between the carbon and carbon, all of those little C's tied together, is where we're storing light energy. That's where we've taken the carbon out of carbon dioxide and turned it into this long string of carbons that are now carrying energy that we could then break apart within our bodies to release that light energy. You've heard of unsaturated fats, and that maybe those are better. Naturally occurring unsaturated fats are things like you'll find in a olive oil or some of these alternative oils to the animal kingdom. The animal kingdom makes mostly saturated fats. The plant kingdom makes mostly unsaturated fats. And so the unsaturated fat is missing the hydrogens off of a couple of those carbons. So delete 2 hydrogens off of 2 carbons and you end up with a double bond between the carbons, and that gives a bend to the molecule. The way in which saturated fats are stored within our tissues and process is typically in a pretty dynamic and diverse environment, so that you don't get plaque buildup or stacking of those into something that would look like a glob of oil. But if you put in a bottle of just saturated fat, it quickly kind of organizes it into a solid, right? So the electrical charge in there. And so if you think about cooking bacon, all the saturated fat comes out of that, and you got all that oils there, and then you set it out, and at room temperature that congeals into this white kind of lard-like structure. That is saturated fat that organizes electrically into kind of this low state of going into a solid, a room temperature transition to solid from liquid. Unsaturated fats will store at room temperature without combining electrically into a solid because of the bends that are in those carbon molecules. And so you can store your olive oil in there in the kitchen, and it will never turn into a solid at room temperature. There's other examples of like a coconut oil and such that will have 2 parts. You'll have some saturated fats, some unsaturated fats, and some will be liquid, some will be solid at different temperatures. And so you can get different amounts of unsaturated and polyunsaturated oils within different plant compounds, where you'll have different melting points with the solids that would form there. One of the most common ways in which fat is delivered from food into the body is in the form of triglycerides. And as you can see in the upper right there, your triglycerides are these 3 different saturated fatty acids that are then lined up on a short carbon molecule called glycerol. And so in the blue highlight, you got 3 vertical carbons all saturated with hydrogen. That's a glycerol molecule that then binds to 3 fatty acids, and that's called triglyceride. And so triglyceride is a common way in which, especially in meat sources, will deliver fatty acids into the body. Now I want to show you a saturated fatty acid molecule as seen before next to a glucose molecule. And so on the left, the saturated fat, on the right, the glucose, and in both of them you see a backbone of carbon line up there. And on the carbon in the glucose, the only difference is the amount of oxygen there. And so suddenly you've got oxygens, one oxygen molecule that's interlaced with the carbon-hydrogen relationship at each point of the carbon chain. And so the difference between a fat and a sugar is simply how much oxygen is present. But keep in mind and remember that both fat and sugar have the exact same potential energy within the carbon there. You're not going to get energy out of the oxygen and the hydrogen on either of these molecules. You're going to get it by releasing the carbon that's in that central chain. Glucose, when it's given the opportunity to be in its natural state or even in an extracted state, will typically not stay in that string, but will actually combine into a classic carbon ring. And so it'll be kind of that long strand will bend itself into a ring shape, whereas the saturated fat tends to not bother bending because it doesn't have the oxygens to create the bend. So because of the presence of all the new oxygen on that chain, you'll go to a ring type structure. And there's three basic, simple sugars in the body, which are glucose, galactose, and fructose. All of them are ring structures that are there. But it's interesting to note that both fat and sugar, carrying the same number of carbons per gram of either, actually have the same calories per gram. And so for both fat and sugar, you're looking at about 9 calories per gram. And so for every gram of sugar, you can multiply by 9 and you'll get the number of calories. Same thing for fat. Because ultimately, the caloric energy within that food, the amount of light energy that can be released from that food is going to be determined by the amount of carbon bonds that are going to be broken. The way in which we determine a calorie is we take 1 cubic centimeter of water and we determine the amount of heat energy necessary to raise it 1 degree Celsius. And so 1 cubic centimeter water increases by heat temperature by 1 degree Celsius, that's 1 calorie. And so when you take 1 gram of glucose or 1 gram of saturated fat, you're going to be able to increase that temperature by 9 degrees Celsius. So you're getting 9 calorie points out of there. When you now think about the fact that your body is supposed to get in 2,000 calories a day is what our usual recommended dose is as Americans, note again that Michael Phelps doesn't eat 2,000 but 9,000 calories a day when he's in competition. There's a huge disconnect between what the USDA is telling us we should eat and what our optimal metabolic base rate is capable of being. And so I believe that all of us are walking around at about 1/4 of our full potential of metabolic capacity to think, to fuel, to move, to be creative. I think humanity right now is running at about 1/4 capacity. And so 25% of our capacity, and occasionally we see these athletes that learn to really push the paradigm into their full metabolic capacity as a human organism. So here we are at 2,000 calories a day, but it's interesting to think about that original definition of the calorie here. You're heating a single cubic centimeter of water 2,000 degrees with that input. And so now you extrapolate that through the body, and much of the energy that you end up burning in a day has nothing to do with how much energy you're burning at the brain or the muscle. It's actually maintaining core body temperature. To maintain my core body temperature at 98.7 degrees Fahrenheit, I have to put a lot of calorie burn in there to make sure I'm heating the water all the time because I'm constantly cooling with the ambient temperature. And so it's an interesting thing to think about, and when you're thinking about energy burn. One of the techniques that we tend to use in athletes to increase our metabolic rate is dropping their temperature. When you do a cold plunge, your body suddenly realizes it needs way more energy release, and so it will actually start putting the little mitochondria inside your cells into a proliferative phase where they'll start reproducing. So you might start reproducing mitochondria so you can get more and more energy production, more and more electrical release, more heat energy to release from carbon bonds from fat or sugar to maintain core body temperature. So just 2 or 3 minutes of very cold water exposure can suddenly induce this stress response of, oh my gosh, we need more energy, and you can increase that basal metabolic rate with that cold water plunge. And so this is a new tool that's been really recognized over the last couple of decades and is used extensively now in elite athletes. And of course, the biohackers have jumped into this and all of that. We've got this cool method of realizing that core body temperature is a huge determinant of your basal metabolic rate. Now consider your day. Are you walking around in an air-conditioned house at a temperature of 73 degrees and you get into a car and you adjust the temperature to 73 degrees, which happens to be skin temperature. So 73 degrees is the temperature at which skin will naturally regulate at a core of 98.7 degrees. All of the way in which blood flow is controlled to the skin will maintain a skin temperature around 73. That's why when you walk into a house at 73 degrees, you neither say it's cold or hot. And you're like, oh, it feels good in here. Suddenly gets to 78 or 80 degrees, and now you're like, it's hot in here, and your skin is having to dilate the blood vessels to get more of your core body temperature to release out of the body to maintain core body temperature. In a cold house, you clamp down the skin to maintain heat in the core body. And so this is an interesting way to go beyond exercise, to think about how could you increase your basal metabolic rate and to allow your body to actually adapt, even over short periods of time like a cold plunge, to cold temperatures to increase the metabolic demand in your body. And so as we start to think through the definition of a calorie, we realize we're really talking about temperature regulation as much as we're talking about energy for muscle or brain or anything else. Once again, I want to drive home saturated fat, glucose per gram, exactly the same amount of energy, because they are ultimately the same source of energy, which is carbon bonds. So where do those carbon bonds end up? So it turns out that both glucose and galactose and fructose and fatty acids of all shapes and sizes, saturated, unsaturated, all of these, none of these can actually be used by your human cell to produce energy, which I find phenomenally interesting and gets into the origin of life on the planet and all this philosophical, interesting stuff that we don't have time to get into. But I find it phenomenally fascinating that there was no multicellular organism on Earth that could have survived without this tiny little bacteria called the mitochondria. The mitochondria is a combination of two different bacterium that consumed one another a few billion years ago. And so the outside structure is basically an archaea. The archaea are a class of bacterium that are highly tolerant to a lot of different caustic environments. And so the archaea, first bacteria on Earth, many believe are able to survive in like the sulfur pits of the weird milieu of minerals in mineral pools, volcanic material, all kinds of different kind of caustic things, sulfuric acid, hydrochloric acids. They can survive in these incredibly diverse areas. And so these archaea, as this super resilient kind of form of bacteria, at some point managed to consume a methane producing bacteria. And so you get a whole methane-producing bacteria sitting inside of an archaea, and they started to learn how to interact together. And so these two very differently specialized membranes of bacteria started to develop unique structures once they were combined into a single structure. The most unique thing that the mitochondria allowed for was a transition from fermentation, which is an anaerobic production of carbon energy into electrical energy release, to this oxygen present, this form, or aerobic metabolism. And so suddenly we could produce energy in oxygenated environments. And the unique thing about the whole structure of taking carbon in the context of oxygen into energy is it's about 10 times more efficient than fermentation or anaerobic digestion of carbon molecules. And so what happened was there was a huge new potential for life on Earth that allowed for the emergence of multicellular life, which is far more complicated and far more energy intensive than the single-celled life that you would find in a bacterium or a yeast or something like that. And so we had this new potential for life when, miraculously we had the emergence of the mitochondria that could then start to fuel larger structures around them with an enormous amount of energy. So the eukaryote, the multicellular creature, ended up absorbing mitochondria into their life form. And so that was the emergence of plant life and ultimately animal life and ultimately the mammals and then humans. We are heavily reliant on these little bacteria inside of our cells. And if you go to any biology textbook or God forbid you go Google it, and you say mitochondria, they're going to show you a human cell with like 2 or 3 mitochondria floating inside of it, and they say, hey, this is the power plant of the cell. And then it'll show you like a cutaway of one of the mitochondria to show that it's a double-walled kind of 2-bacterium kind of structure and all this. They never mention that it's a bacterium, which I think is a real discredit and a lack of reverence to the microbiome that I get frustrated about, but that's a side, probably personal problem. Nonetheless, the mitochondria, these bacterium inside there, are depicted as 2 or 3 in each cell. There could not be a more ridiculous underestimate of our potential life than that diagram, because in every single human cell, we're closer to 200 mitochondria in the cell. And the mitochondria are big enough that once you get to 200, you have literally packed full the entire cytoplasm of the cell with these tiny little bacteria. And they are bacteria. They have their own DNA, that looks much more like a viral genome. They have very simple, typically only 30 little genes instead of our 20,000 genes in the nucleus of the human cell. But you have all of these unique, genetically unique mitochondria living within inside your cells, and they can proliferate. Just like bacteria grow in a petri dish, your mitochondria can divide and proliferate within your cells, irregardless of whether your cell is dividing or not. And so it's a very cool thing that these bacterium have learned to be such an integral part of biology that we've actually forgot them to be something separate, some source from the microbiome, and we take them on as if they are human cells or machinery within the human cell, being human in nature, and they really just aren't. They don't behave anywhere near what we do. But the reason we could never survive with these guys is because the human cell does not know how to use sugar and fat to produce energy. It can't break those carbon bonds through any other mechanism, so it waits there until the mitochondria, consuming the glucose and fatty acids that are pouring into the cell from your bloodstream, it's waiting for the mitochondria to take those up and turn them into carbon dioxide. By taking that long carbon chain, releasing all the electron energy within that long chain of fatty acid or glucose, you release the light energy. So the purpose of mitochondria is to create sunlight within your body, which I think is just eloquent and beautiful, and it gets me excited and in a state of awe over my mitochondria. Nonetheless, as the mitochondria is doing this, it doesn't want either fat or sugar. It can't use either of those molecules, which is pretty darn extraordinary. To start to think that we've spent such an enormous amount of time of media attention and women's magazines and science and develop of diets and diet industries and keto guys and paleo guys and all of this BS around argument over who should be eating fat and what sugar and protein and what should we eat. My gosh, everybody's got a different opinion. In the end, we can absolutely use none of it as fuel. Sugar and fat are not the fuel that turn into the release of carbon energy within the body. First, it has to be turned into an incredible molecule called acetyl-CoA. Acetyl-CoA is the combination of an amino acid building block with the output from 2 enzymes that have turned both the saturated fatty acid and the glucose into the identical molecules that are now infused with nitrogen. And so you take saturated fat with carbon and hydrogen, or the glucose with carbon, oxygen, and hydrogen, you put it through a single enzymatic step at the beginning of its absorption into the mitochondria, and it suddenly has nitrogen infused on it and phosphorus infused. And this nitrogen-phosphorus combination with an amino acid turns into this large molecule called coenzyme A. Pictured here, you can see how radically different that molecule is from either the simple glucose or the simple saturated fat. So we develop in a single enzymatic step this complex storage of carbon energy that can then go on to metabolize into light energy within the mitochondria. That process is taking place in something called the Krebs cycle. And if you're anything like I was in college, I have severe PTSD memories of the Krebs cycle. I hated memorizing this thing, memorizing all those enzymes and all the different structures coming off, and the FAD and the NAD and the NADH and the FADH and all these metabolites. It was so confusing and never made sense to me at all until I finally got to the point where I was starting to understand nutrition as a carbon source rather than all these other molecules. The long and the short of the Krebs cycles is taking that complex molecule of acetyl-CoA and converting it into ultimately ATP, or adenosine triphosphate, which is pictured on the right here, which is this phosphorus, ribose, and another form of carbohydrate, and the the amino acid structure there. And so the ATP is a final carrying point of the downstream breakdown products of acetyl-CoA to be an energy release system. And at the point of ATP function, we start to release the electrical energy from that final carbon bond structure of glucose and fatty acids. And in that final structure, you see far less carbon content because we've released so much of it as CO2. And so we create ATP and CO2 and water as the main byproducts of the Krebs cycle as we release the carbon energy from the original glucose and fatty acids that had entered the cell and then were transported into the mitochondria by acetyl-CoA and release that. So it's a beautifully complex process, and I just marvel at the complexity. You start to really question again, what is the origin of life? How did this level of complexity of function and structure and breakdown of light energy and the buildup of CO2 into light energy within a plant, then within food, then into a glucose molecule and into a fatty acid, and then to then depend on a mitochondria to come out of nowhere to come and digest that back into light energy so that the very first multicellular organism could occur. It is so eloquent. It is so beautiful. You and I do not have the cognitive or intellectual capacity to imagine the miracle of life. Life is so much more miraculous than anybody can ever tell you. And if they're going to dumb your life down, your life experience of energy release down to a diet, there is a serious problem. And so I want to break your relationship to any form of diet industry. And that includes your identity as a vegan or a paleo or just an omnivore, American, whatever you identify yourself as, that identity is a real problem. Food as fuel is as far as it should go. If I start to say that I am a vegan, I have dumbed down my entire intellectual capacity to be a spiritual being, connect with consciousness, move into a knowledge field of co-creation with the universe, and I have now embodied myself in a description of the sources of micro and macronutrients that I'm willing to consume, and that's who I am. It's so fearful how we are able to put labels on things, on little tiny philosophical beliefs around food and then screw up our entire relationship to the food through that. And we have emotional connection once we do that, right? Once you say, I am a vegan, there's a little bit of judgment to everybody else around you, especially those people that keep asking, where do you get your protein from? You're pretty much ready to shoot those people. And so there's this frustration that emerges, there's hostility that emerges, there's a sense of guilt that emerges from people who are in conflict. It's very much how religion can take spirituality into a polarized environment. And so I want to free you up of that. If somebody starts talking about what diet they're on or who they are as a vegan or a non-vegan or whatever they are, I want you to just rise above that conversation. Just float above it for a minute. Connect to spirit. Imagine the sunlight powering a plant to take carbon out of the atmosphere in the form of CO2, to power it into long chains of carbon that are now being carried through your bloodstream to this extraordinary garden of mitochondria within you, this massive bacterial microbiome within you that's going to release that light energy again. Take yourself through that process a couple times and then focus back in on the conversation and have a light spirit about the whole thing. There's no reason to have any heaviness about who you are, what you eat, anything else. This is an opportunity to put you back in a spiritual relationship with the gift of biology on the planet, which I can't find a bigger gift than the food system itself. We were created as Homo sapiens to be sensory beings. I was recently told by one of my intuitives that I work with that I should start studying the hedonism as a science. And when I first heard that, of course, maybe it's just a male brain problem. I'm thinking, is that something about sex, or am I not being creative enough in the bedroom? All those funny things go through my head. And so it's weeks before I get to this because as a typical American male, I'm probably insecure about my sexuality on some level and everything else. I'm thinking, why am I having to study this? Like, I'm so good at this biology stuff over here, and I love my microbiome science. Why am I going to go study hedonism? Finally, came up, and I knew I was about to see her again, and I knew she was going to ask if I had looked into it, and so I started looking into it. And the first book that pops up for me is, of course, Epicurus, who was a Greek philosopher. And Epicurus had decided in his philosophical view of the role of humanity on the planet that our highest purpose, the highest vibration and purpose of humanity, was to experience pleasure. And the way in which he explored this was through food. And so, of course, his name, Epicurus, became the root of the science or practice that we now call the Epicurean there, or those that are curious about food. The Epicurean is that kind of foundation of the realization that Epicurus came to, was that if you look at the functions of the human brain, it's entirely a sense organ, right? And so we are a sensory system that can walk around and we can do things and all of that, but it seems that the only purpose for doing anything is so that we can see something, taste something, feel something, experience a sensation of some sort, smell a rose, see the rose, give the rose to somebody to have another experience of their smile when that hits our neurologic system, when we see that smile. And so deeper I dove on Epicurus, who of course his whole philosophy became known as what we would then know as the field of hedonism. That kind of was another philosophy that emerged in the following couple hundred years. But hedonism is the whole concept that we are incredibly designed to experience nature. And perhaps most of all, incredibly designed to experience food, perhaps better than any other animal on earth. And so that is fascinating to me, and I think it's where I want to kind of end this kind of thought process for you as you're starting to think about a different relationship to food. Is your highest purpose, your highest vibration to observe and experience the beauty of nature is through your connection and sensory experience of that nature, and your food is an incredible source for that. To give you just a little bit of contrast to that, I want to take you over quickly to a thought process on sugars here. And so as much as we've confused fat for the fat that we accumulate in the body, when in fact that's just the formation of stress-inducing fat storage because of a sense of adversity, a sense of scarcity. So we start to store sugars and fats as peripheral or visceral fat. All of that's there. But I want to do a little bit of a dive on sugars here. The sugars that we covered there, I kept showing you glucose, but they come in 3 different ring structures. Again, because of the oxygen that's now on that carbon strand that you would normally have straight in a fatty acid, it creates these ring-like structures. And so glucose has got a 6-carbon structure to it. Fructose is 4 carbons and an oxygen in a ring. And so you've got carbon and glucose that then can combine into what's called a disaccharide through a combination of oxygen binding that then gives you these 2 rings, and that's called sucrose. And so the single monosaccharides that we have in the bloodstream, the single sugars are glucose, fructose, and galactose. And then when you start to put them together into different combinations, 2 of them together become sucrose. And sucrose, again, is common in plants, and that's the typical sugar in something like corn or whatnot. And then we create high fructose corn syrup when we break those molecules apart through an enzyme process to create then combinations of monosaccharides, both glucose and fructose in combination, a single liquid. Nature doesn't like that. Nature, if it sees glucose and fructose, will typically create the disaccharide sucrose from it, which has a lower glycemic index. If you have purified glucose or purified fructose, you have a relatively high glycemic index. Of the 2, glucose is the most potent. Glycemic index is the amount of blood sugar that it reads in the body. So in glucose, it's actually 5 carbons and an oxygen, and in fructose, you're 4 carbons and oxygen. So there's less potential energy in the fructose than the glucose molecule. So we consider the glucose at this higher glycemic index, this higher sugar energy content than you would from the fructose. Nonetheless, the body likes to decrease that whole glycemic potential by starting to string these together so that it can't be metabolized as quickly. It slows the movement of carbon release in the bloodstream when you consume something with sucrose in it rather than a purified sucrose, fructose monosaccharides. Most of the sugar in plants, which I find amazing, are actually polysaccharides, where they start to line up these very long glucose molecules. And so all those 5 carbon rings with the oxygen making the completion of the ring, those glucose molecules can line up into these complex superstructures that we call starch. So when you eat a potato, you're eating a vast amount of glucose potential energy, but it's in such a form that it actually breaks down completely differently in the body. It's a very slow release of energy, and so when you eat a sweet potato, your blood sugar is not going to spike as it will if you eat the same number of calories of simplified sugar that's stirred into your coffee in the morning. And so simplified sugar releases its energy very quickly, and spikes of sugar can occur in the bloodstream as it's released very quickly from the liver and the rest. Polysaccharides, these large starches, for example, can be very slow release energy forces for the body. And so if you haven't read, I think it's McDougall's book that's the starch secret, and he really points to being able to reverse diabetes by giving these whole starch sources to people who have now identified themselves as diabetic or somehow sugar sensitive. You give them an entirely carbohydrate meal in the form of starches, and they actually get less insulin resistance. They actually lessen their diabetes rather than increase their propensity for it. It goes far beyond the beauty of starches. So these are some other examples of naturally occurring polysaccharides in the body, and most of these are considered fibers. And so cellulose is the most common of these. These occur in whole grains, green leafy vegetables, beans, peas, lentils, you go on down the list. And cellulose is this beautiful structure that is not absorbed at all into the body as you would with starch and glucose and fructose and sucrose and all those. Those are absorbed very quickly. Instead, these large dietary fibers, especially the insoluble fibers, stay in the gut and function as a compost source for the bacterium of the gut. And so these act as incredible accelerators of microbiome diversity and ecosystem and all of that. And so it's critical that we get more fruits and vegetables in our diet so that the carbohydrate we're consuming is what we call complex carbohydrates. So all of these on this list would fall into that category of complex carbohydrates. Simplified carbohydrates would be the glucose, galactose, fructose, sucrose as well. So the polysaccharides are this super power-charged source of life within you as the microbiome starts to thrive inevitably on this journey into the breakdown, the slow breakdown of these carbon chains rather than the quick release in the form of simplified sugars. Inulin is an interesting one, a naturally occurring one in wheat, onions, chicory root, leeks. This has become a food additive known as a prebiotic. I am not a fan of prebiotics because they have divorced these long chains of polysaccharides from their original complex of other forms of fiber, as well as starches, as well as simplified fats and sugars that originally came in that food to deliver the perfect match of microbiome to micronutrient delivery systems and all that. So anytime we take something that's good and then purify it, we tend to screw up the way in which it's used in the body. And I really believe that happens when you're taking high concentrations of inulin as a prebiotic or something like that. And so I'm a huge fan of consuming these in their original form, in the onions you're cooking, the chicory root, the leeks, all of these different compounds. So that's the right source for something like inulin. Inulin, interesting, is a long chain of fructose and glucose. And so it's a longer chain version of the sucrose disaccharide. Keep adding those together and you end up with inulin, which never really gets absorbed as a sugar for the bloodstream. Instead, it stays in the gut and breaks down slowly to fuel the bacteria in the gut to a bigger biodiversity and a more vigorous life cycle there. Beta-glucan, pectin, psyllium husk, all of these are roughage within the food that we consume, and they play different roles within the diversification of the bacteria in your gut. And everybody has probably heard that cardiovascular disease and cancer is radically changed in its risk profile if you consume more fiber. And so the fiber, what we call fiber being these long polysaccharides, are carbon sources for the microbiome, not for you. And it's important to realize that 90% of the enzymatic work done in the human body is not done by a human cell at all. So everything we've talked about the coolness of mitochondria, releasing energy for the human cell, that's 10% or less of the energy activity within the body. 90% is done by the bacteria within your body. The bacteria on your skin, the bacteria within your gut, the bacteria within every single organ system. And so we have bacteria teeming all over the place that are doing 90% of the work in the body. And these polysaccharides are their best source of nutrient. They don't have mitochondria in them, so they don't do any of that aerobic experience. They need a fermentation process of these long polysaccharides for their fuel source. And so eating fruits and vegetables is the only way that you really fuel energy there. So when you hear some paleo person talking about all the meat they eat and everything else, you know they're lacking all of the ideal foods for their microbiome. So they're going to become microbiome deficient over time, and they're going to start to rely more and more on fermentation of proteins, which is a very caustic process for human biology. And so meat without carbohydrates is really damaging to the system and undermines the vitality and biodiversity of your microbiome. And so as a plant-based dude, I just freaking love plants of all sorts, sizes, all of this, because I know that the primary purpose is not even for my cool mitochondria in human cells. It's for the 6 pounds of bacteria that I carry around in my gut that are going to do most of the work that I need done in a day. And so they're going to detox my body. They're going to do a lot of the metabolic, clearance of toxins. They're going to prepare all of the bioavailability of the nutrients I'm going to ultimately absorb and someday pass on to those mitochondria and the rest. And so I want you to start to really just appreciate the abundance that lies in the carbohydrate world, especially the complex carbohydrate world of the fruits and vegetables that you're consuming on a daily basis. And you'll notice if you go down that list of sources for these polysaccharides, none of them are animal sources. All right, so stepping forward again, looking at the ways in which we have dumbed this thing down. So we've gone from those long polysaccharide chains and starches and all of this down to simplified sugars. And one of the frightening things that's very hard to find teased out in the literature, the last article I really read on this was almost 20 years ago now, but the process of enzymatically breaking apart the disaccharide of fructose and glucose, that is the form of sucrose, that's naturally occurring in corn. And when we break that apart into high fructose corn syrup, which is a combination of the monosaccharide glucose and the monosaccharide fructose, the fructose is actually in the mirror image of what it should have been. And so a naturally occurring fructose that you would find in an apple, for example, it's in the D-fructose shape. And these look like the same molecule left and right here, with the exception of that OH group at the bottom on that last carbon. And so what it's showing you is they are the mirror image of one another. The D-fructose and L-fructose are the mirror image, but they can't be set on top of each other because they actually aren't the same molecule. They have actually a different bend in their structure due to this hydroxyl group on the opposite side of the carbons. And so when we create high fructose corn syrup, we're giving you a simplified sugar that is of the wrong shape. And the result is pretty bizarre. Instead of being able to be processed as a monosaccharide sugar, when you drink a high fructose corn syrup soda, you go get a big gulp or something like that, and you just consume 400, 500 calories of high fructose corn syrup. And if you continue to measure the blood sugar over the next hour or two, you find out there's no blood sugar excursion. The blood sugar never shoots up, which as an endocrinologist was frustrating when I first saw those studies. It's like, wait, is this like some sort of super diet food? Like you can actually consume as many calories of simplified sugar as you can, and you never raise your blood sugar? Whereas if you drink, or just eat an orange, your blood sugar goes right up because it's D-fructose. D-fructose goes in the bloodstream quickly. So what's happening with L-fructose remains really a bit of an unsolved puzzle in science right now. But what we do know is that the pathway that it follows metabolically through the liver releases triglycerides from the liver. And so you get a cholesterol response, a triglyceride response from consuming high fructose corn syrup instead of a spike in blood sugar. And so it's a very bizarre situation with L-fructose where the body is so confused as to do with it, it sends out a stress response of cholesterol. Triglyceride released in the bloodstream is a stress response from brain to peripheral tissue to liver. And so we're inducing this chronic stress response with high fructose because it's a non-natural occurring shape. Same overall molecular content, same number of carbons, oxygens, and hydrogens, but it's the mirror image of the original origin fructose that you would find in an apple. So that's kind of your world of high fructose corn syrup. And then of course we had to go one step further when it was like this huge press to get sugar out of sodas, and they came up with NutraSweet or aspartame. And NutraSweet is a compound that has almost no resemblance of a sugar in its original thing. In fact, it's an alcohol. And so aspartame or NutraSweet is aspartic acid combined with an amino acid called phenylalanine, which is one of our essential amino acids, and methanol. And so it delivers methanol, and the overall experience of this molecule when it touches the tongue is it triggers the same sensory response of sweetness. And so it's a boon that we can have a sweetener that was not a complex carbohydrate or simplified carbohydrate at all, but was instead an alcohol. Alcohols are a form of carbohydrate, of course, but they don't have the same structures of any of the saccharides, mono or otherwise, that we've discussed. The scary thing about aspartame is that when the aspartame hits the liver, similar to the confusion that it gets when when it takes the L-fructose from high fructose corn syrup and turns it into triglycerides. There's no sugar excursion that happens when you drink NutraSweets. It looks like, okay, perfect diet sweetener, gives you this sense of a sweet soda without your blood sugar going up. Great, that's good. But the downside is when this complex molecule goes and metabolizes through the liver, it releases methanol from the overall structure. Methanol is also referred to as wood alcohol. It's a common alcohol that can be made when you don't run an alcohol still correctly. And so one of the common phenomenon of the bootleg liquor industry in the early 1900s and all of this was that a lot of these stills being run in backwoods of West Virginia or whatnot were not being set up correctly, and they were getting, instead of ethanol, they were getting methanol, wood alcohol. And these guys drinking their own wood alcohol would suddenly develop blindness, because it turns out that wood alcohol is a potent toxin to the neurologic system specific to the way in which you see the world. So if you really want to screw up, the way you see the world and your ability to see the beauty of it, drink a lot of aspartame. But it actually gets grosser than that, is that once the methanol goes back through metabolism in the bloodstream and hits your liver a second time, it's turned into formaldehyde. And so at each step you can see the massive simplification of this small carbon molecule as it moves from this complex aspartame to methanol to formaldehyde. Your body is trying to break this thing down into something that it can deal with. Formaldehyde is something that it can deal with because it's a fat-soluble toxin, and it can push it out of the bloodstream into fat cells to keep it away from the blood vessels, because it's a very caustic compound. If you've ever gone through gross anatomy in medical school or otherwise, and you smelled all those fixed bodies all that time, one of the main chemicals, of course, in there is formaldehyde. So we stabilize the decomposition of cells by pooling them in formaldehyde. That keeps the body from being able to exchange hydrogen and oxygen that would lead to the decomposition of the carbon substrate of your body. And so formaldehyde kind of freezes metabolism altogether. It kind of blocks the ability for anything to break down. So if you soak a body in it, it won't decompose as quickly. But on the bad side, if you're drinking a lot of NutraSweet containing beverages, a lot of diet sodas, you are preserving your fat in such a way that it can't mobilize. And so you're locking a toxin that shuts down metabolic capacity and exchange of information and energy inside those fat cells when it fills with formaldehyde. And so, I recently saw Bill's Brain on Netflix. So you got, wealthiest guy in the world, in the universe, whatever he is now, and you've got Bill consuming insane amounts of diet soda the whole time. And so there's a part of me that wonders if there's not a maleficent bone in his body, but he's so full of formaldehyde that he can't make any sense of the world that he's living in, and he's in a fight or flight state to try to figure out how to solve for humanity's problems and coming up with all the wrong answers because he's got so much formaldehyde in him. Well, whatever happens to Bill, what I can be confident is when he passes away, his body's going to decompose slower in the grave than mine, and so maybe that's his victory. He will be longer lived in the grave than I will be. I will be worm food before I know it. And so in this bizarre way, as we consume a massive amount of formaldehyde through our artificial sugar systems, we're shutting down the ability of those fat cells that are now storing that fat-soluble toxin to get back in the game, to release their fatty acids back into the game and release energy. And so we're gumming up the system. And so if you have to kind of back up for a second and wonder why we behave as we do as humans right now, why we are sitting on couches, sitting around, eating alone, becoming more and more obese with every passing decade, it's because of this incredible mix of chemical dependence that we've created as we have created so much fear of fat, cholesterol, salt, sugar, and the rest. We have created so much food fear that we have adopted a purely chemical food system that functions as a drug delivery system so that we become more and more dependent upon it over time, and metabolically it keeps slowing us down more and more, such that a revolution seems unlikely. We are too exhausted, too fatigued. The number one complaint in all primary care offices throughout America now is chronic fatigue and sleep disorders rather than the back pain that used to be our problem. We used to have back pain because we had financial stress and stress around the family, as we can discuss later, and things like that. But right now, our crisis is one of a lack of fuel at the cellular level because we have lost our true connection to sunlight through our carbon matrix.
Hey, I'm glad you enjoyed this lesson. We have more lessons on the way, so click the notification bell below so you don't miss our weekly videos. I'll see you there.